Good afternoon, everybody. So today we're going to talk about section 3.10, forced mechanical vibrations. So previously in 3.6, we had talked about what happens when we have unforced mechanical vibrations occur. And so we have this homogeneous linear equation where m is the mass of the object, gamma here is our dampening coefficient, and k is the spring's constant. So what happens when we apply an external force? Well, then this switches from a homogeneous to a non-homogeneous, and it goes to the following. M sub y double prime plus gamma y prime plus ky is equal to our external force F sub t. Okay? So again, sometimes you'll see the subscript of an E to talk about external force. A lot of times just because of trying to keep up with those, we'll drop the E off of that. So when we say big F sub t, we are talking about the external force that's being applied. So again, M is equal to the mass. Gamma is equal to the dampening coefficient or damping coefficient. Sorry, damping constant in that case. And K is the spring's constant. Okay, so first of all, we're going to look at a very special case here with resonance where there's no dampening. And then we're going to go over a very specific example, which you see over on the right-hand side of the board. And this is the only one that we're going to go through, but I'm going to talk about the other cases that occur. So what happens, well, if we let gamma equal 0, that means there's no dampening that's going on in the system. So that means we get something of the form y double prime. And yes, there is a little bit of change in notation. I'm going to talk about that here in just a second. Plus omega sub 0 squared y, which is equal to f times cosine of omega 1 of t. So the reason that there is a change here is we're talking about, actually, let me change that just a little bit. This is omega sub 0, okay? So the reason that we're going to deal with this is here we're actually linking the omega inside of this function and also the spring's constant. And what we're saying is the spring's constant is square of this value. And how we got omega, this is actually coming back from 3.6 as well. So omega sub 0 is equal to the square root of k over m. So in that case, k was equal to omega squared divided by m. And so once we divide it by m all the way through, notice that we are getting omega squared. So it's not that we just made this up. This is what we're going to be dealing with. So, and we're also looking at a very specific external force that's being applied. We're looking at a sinusoidal force being applied to our system. Okay, so one important note is now that we know how these values are found, I want to say that our characteristic equation okay, again, that's where we're solving for the homogeneous. This is going to lead us into plus or minus omega I, okay, which means our characteristic equation is going to be of the form C1 cosine of omega sub 0 t plus C2 sine of omega sub 0 of t. Okay? Notice that our g of t, our function here, has a part of our solution here. So what we're going to need to do is we're going to have to say, okay, well, then that means our particular equation is going to be of the form t times our value. So we're going to get AT cosine of omega t plus B of t sine of omega t. All right. The frequency W sub 0, or omega sub 0, of the vibrating system is called the natural frequency. And resonance occurs when the external force is equal to the natural frequency that's occurring. So this is going to actually cause and actually going to build this wave that we're going to be generating when we apply a force to our spring system. Right? And so that's where the idea of resonance is coming from. And you'll actually see that in the graph for this particular problem here in just a second. All right, so let's get on to this problem. These guys are not bad to set up. So here we have a 12-pound weight that stretches a vertically hanging spring 1 foot, okay? And then we let omega equal 0. Sorry, not omega, but gamma. So that means, again, we're dealing with no dampening. And we're going to have our external force be cosine of 8t. All right, we're going to assume that the external force is applied to the weight from its natural resting state of equilibrium. So what we've done is we've set that weight onto that spring, we let it stretch it out, and then we let it rest, and then we're applying the force to it. So first of all, I want to set up the IVP, and then find a general form of the particular equation and the characteristic as well. All right, so first of all, to set up the IVP. Well, since we're applying this after it's at a state of rest, we're going to assume that y sub 0 is equal to 0 and y prime of 0 is equal to 0. So no force is being applied to it. Nothing is happening when time is equal to 0. All right. The next thing is we need to set up our equation before we can get into y sub c and y sub p. All right. So first of all, we have m y double prime plus gamma y prime plus ky is equal to cosine of 8t. All right. So we need to find all of our values. The nice thing is we've been told what gamma is. So since we have no dampening, gamma is equal to 0. So let's go ahead and state the things that we know. All right, well, we're dealing with the standard system here. So we have 12 pounds. That's the weight of the object, not the mass. So this is something that you have to be careful on when it comes to these problems. Okay, so we need to find the mass. Well, the nice thing is mass is equal to the weight of the object divided by gravity. So in our case, it's 12 pounds divided by 32 feet per second squared, which this is going to give us a value of 3/8. And that would technically be slugs in that case. So again, a slug in the standard system is a measure of mass like kilograms is in the metric system. All right, now we need the spring's constant. Well, that one we have to be a little bit careful on. The nice thing here is everything is given in feet or pounds. So foot-pounds, everything's going to work out nice and neat for this. So we have a force is equal to kx. All right, finding the spring's constant. And so here, force is equal to 12. The distance that it was stretched was ½ a foot. And we're looking for k. So our spring's constant is equal to 24. All right. So now we have these nice clean values that we're dealing with. So let's plug this all in. Okay. So we have our mass of 3/8 y double prime. And I'm going to put this 0 here just to show that we're plugging this into the appropriate spot. Plus 24y is equal to cosine of 8t. All right. So let's simplify this. In order to start solving for either y sub c or the particular equation, we need to get y double prime by itself. So let's multiply all the way through by 8/3. So that means I can go ahead and drop this. So y double prime plus, well, 8/3 times 24, that's going to give us 64y, which is equal to 8/3 cosine of 8t. Okay. Again, we set up our IVP. We now have our differential equation that we're going to solve for. So now we have everything that we need. So let's go ahead and set up our characteristic equation. So we're going to first find y sub c of t. And the reason that we're finding that is because we need to make sure, if we are going to get a repeat of what's in here, we need to make sure that we do that before we find a particular solution. Okay, so we get lambda squared plus 64 is equal to 0. Got a little ahead of myself on that one. All right, and then we solve this. So we're going to get lambda is equal to, well, negative 64, and then we're going to take the square root. So we're going to get plus or minus 8i. So that means alpha is equal to 0, and beta is equal to 8. All right, for those that need a refresher on what we're looking for whenever we get a complex variable, our y sub c, or complex roots here, is e to the alpha t times a cosine of beta t plus b sine of beta t. All right, our alpha is equal to 0, so that means this term here is going to go to 1. In our case, we're going to have, and I'm going to change these a's and b's to c1 cosine of 8t plus c2 sine of 8t. So that is our y sub c. Okay? So nothing horrible there. That's pretty straightforward. We're done with that piece. Now, the big thing comes in. We need to see or make sure what we're looking at for our particular equation. Well, since we're looking at this function here, cosine of 8t, well, this goes back to 3.8 when we were dealing with constant coefficients, so the undetermined coefficients process. So since our cosine of 8t is also in our answer, that means when we find y sub p of t, our particular solution, we need to multiply it by t. Okay? So now we find y sub p of t. Again, since g of t, which is equal to cosine of 8t, is in y sub c, then y sub p of t is equal to at cosine of 8t plus bt sine of 8t. Now, we would say, hey, we're done. We got a generalized form. Well, that's not good enough. When we're solving for a particular solution, we are solving for a particular solution. So we need to find out what A and B are. So that means we need to plug this back into our original, our differential equation, to solve for A and B. So that's the next step. And this won't be too hard. I always like to go a step further, so this is going to go solving through this. So we can use this and say our general solution is just this addition of these two and we'd be done. But I want to go one step further with this to show what we're looking for. All right, so when we solve, we need y sub p of t is equal to at cosine of 8t plus bt sine of 8t. I don't need the first derivative, but I need the second, so I need to go ahead and find the second for that one. All right. E of t is equal to, first times the derivative of the second, so derivative of cosine is negative sine, so we're going to bring in negative 8 at cosine, or sorry, sine of 8t plus a cosine of 8t. And then here, when we take the derivative of sine, we're going to get cosine out. So we're going to get plus 8bt cosine of 8t plus b sine of 8t. All right, and then we need our second derivative. So y double prime of p of t. Okay, first times the derivative of the second. So derivative sine is cosine. We're going to bring that out. So negative 64a t cosine of 8t plus, technically minus. Make sure you keep track of all your signs here. We're going to take the derivative of t, so we're going to get negative 8 sine, or sorry, a sine of 8t. Derivative of cosine is negative sine, so we're going to get negative 8 sine, or a sine of 8t. And then this one we are going to be dealing with the product rule again. So minus 64b t sine of 8t plus 8b cosine of 8t. That's the second, that's the derivative of the first. And then plus 8b cosine of 8t. All right. So now the next step is to combine all of these together into our equation here. So we're going to have negative 64 at cosine of 8t minus 8a sine of 8t minus aa So that's something nice that we have there. So those two combine. So we're going to get negative 16a sine of 8t minus 64bt sine of 8t. And then notice here that we can combine those two guys. So, so plus 16b cosine of 8t. And then finally add 64 to those guys. So plus 64 at cosine of 8t plus 64 bt sine of 8t. And we have this all equal to 8/3 cosine of 8t. Well, the nice thing is do we see a lot of cancellations occur here. So our negative 64 at cosine of 8t, that's going to cancel out. And then our 64 bt sine of 8t, those two guys are going to cancel each other out. So the nice thing is this is just negative 16a sine of 8t plus 16b cosine of 8t which is equal to 8/3 cosine of 8t. Well, notice here, we just match what our existing values are going to be for a and b. So since there's no sine term over there, that means negative 16a is equal to 0 and 16b is equal to 8/3. All right, that means a has to equal 0. So notice that that's going to eliminate that term there. And b here, well, we divide by 16. So that's going to knock out an 8 from the top and an 8 from the 16, leaving us a 1/6. So that means our particular equation now, y sub p of t, is simply equal to 1/6 t sine of 8t. And that's our particular equation. All right? Which means our general solution, okay, is our y sub c, so y of t, is equal to c1 cosine of 8t plus c2 sine of 8t plus our particular equation, which we just stated, is this 1/6 t sine of 8t. and that's our general solution. So what we would do then is, if we wanted to find C1, C2, the nice thing is we have our initial conditions that y sub 0 and y prime of 0 are both equal to 0. And in fact, if you went and solved that, so this way you could check if you would like to. If you solved the IVP, our general solution in the end is simply equal to 1/6. Oops, left my T off here. It's just 1/6 T sine of 8T. And that would be the solution to your IVP. Now the cool thing is we talked about this is a resonance problem with no dampening. So let's see what this graph would look like. And I'm going to insert a good graph here also when we get there. But when we look at the graph, and again, not drawing this to scale, but this is what it's going to appear to look like. And I'm just going out to 4 just to show you what's going on. All right, the graph will look something like this. Now I am going off scale for this. So it's actually starts off and it's increasing out. And in fact, it's guided by this 1/6 T as our enveloping equations for that. And so it's just going to continue out. Now, thinking about this in a natural standpoint, this type of idea of this continuing to increase as it goes doesn't really apply in nature. However, at a certain point throughout this is true. So for a limited value of T, this is true for that part. All right, so in the next lecture, we're going to talk about the 3 different other cases that we have not talked about, where we have dampening, yet there's a difference between the omega that's inside of our external force versus our springs constant, when those are different. And then also what happens when we add dampening to that, and look at how these graphs behave. Because knowing that, then for any of those problems in the Emporium, when you come across those, you'd be able to graph pretty quickly what's going on. All right, so we're back. So this is, again, the second part of force mechanical vibrations, and I'm going to do another video here in just a second, talk about case number 4, because one, I don't want to erase and have to draw the picture and all that fun stuff. So case number 2, so case 1 was dealing with resonance. That's when omega 1 was equal to omega sub 0. And so what happens is we saw that this wave eventually continues in its amplitude as it goes. Again, from a natural standpoint, that doesn't make sense, but from a limited time frame, it does, to see that occurring. So the resonance is equal to the springs, the force of the spring and the external force being applied. So when we have no dampening and these two are not the same, omega 1 is not equal to omega sub 0, then what we have in general is these beats that are occurring. So this is an example of what we call a beat. And so notice here that we start building up and then it dissipates and then starts back up again. So in general, what happens is that the two forces, and the two forces here are talking about the spring's constant, the spring's force, and also the external force. These guys interact, sometimes reinforcing, okay, so that's where we have this buildup occur, and then sometimes canceling each other out, which is what happens around these points here. Okay, so this is what we call constructive and deconstructive interference. So again, as they work together, there is a resonance that occurs, but then all of a sudden they start working against each other, and this is what happens, and then they pick up again. Okay, so they're sometimes working together, sometimes working against each other is what happens. So this is what the graphs would look like if you had no dampening and omega 1 is not equal to omega sub 0. And so the nice thing is we actually saw in our previous example, notice that we had a 64 here and an 8. So there's a real quick way to check, especially if you have no dampening to what's going on there. All right, case number 3, dampening on resonance. So we had this resonance occur that they're working together, except there is a dampening effect on there. And so what happens in that case is these are causing oscillations in what they're called in phase. So that means they are working together. So they're being constructive in their interference. So the spring force and external force are oscillating or causing the oscillations to occur in phase. Let me write that. And so when they happen in phase, this is where the resonance occurs. Okay. However, due to the friction in the system, notice that we start seeing, okay, it does build up like before, like with our case 1, except notice it levels off. So we reach a maximum for the height of our amplitude in that case. So let me write that down. So due to the friction in the system, and again, that friction is caused by the dampener on there, or that dash pot that we talked about in 3.6. The amplitude eventually levels off at a maximum. Okay, or sorry, at a maximum level. All right, so that will finish case 2 and case 3. Again, case 1 was dealing with resonance with no dampening. What happened to it is it continued to build on that graph. Case 2 is no dampening, but there's also no resonance with it. So we get these beats occur where we have constructive and deconstructive interference working with these external and the spring forces. And then case number 3 is dampening on resonance. So they do work in phase with each other, except with that dampening effect, it's leveling off the playing field, if you will, in that case. So the next thing that we're going to look at is case number 4. And so that is dealing with, well, what happens if it does have a dampening on there, but there is no resonance? All right, everybody, we're back for one more video on this. This is part 3. So this is dealing with case number 4. So this is resonant excitation with dampening. So, sorry, non-resonant. So what that means again is we're dealing with a spring system of some sort with dampening. But in this case, when we're applying this external force, the spring's constant is not equal to omega squared in this case. And we're going to see what happens with that. And actually what's really cool about this graph is there is a similar effect when omega is when k is not equal to omega squared and we have no dampening. So notice that these beats do occur. And sometimes these are a lot closer together. I expanded this out just to show you what's going on. But this could happen rather quickly, or could continue out a little bit further. So what's happening here are the spring and the external force are causing the oscillations just like before. So just like with case 3. Okay. The motion of the spring is dampened, which means its effect is attenuated over time. So attenuated means that where we were getting that spring bouncing it back like in case number 2, eventually having that dampening on that is actually going to lessen over time the effect of that. And so eventually what happens is we take over with the external force. So this is the external force taking over. This is the dampening effect in this part of the system working with the external force. So the deconstructive and constructive interference that's occurring. And then eventually, at some point over time, that dampening effect will no longer cause these beats to occur. And then you'll start seeing this happen, where the external force takes over. Okay, and so I'm going to write that down as well. So the motion of the spring is dampened. Sorry, is damped. Which means its effect, the effect of the spring itself, is attenuated. So that's our $10 word right there of the day. Meaning that its effect is lessened over time. Okay, so we start to see the two out-of-phase waves that are occurring, leaving the external vibration after that. Okay. Again, we start to see and here this out of phase is meaning there's no resonance occurring, so it's deconstructive and constructive beats that are occurring, if you will. So two out of phase waves, but one fades out over time. Leaving just the wave of the external vibrations. So again, the effect of the spring is lessened over time, and so eventually whatever that external force that we have is applied to it is what takes over in the end for that part. All right, so that's pretty much all we're going to talk about for 310 for force mechanical vibrations. If you look in your book, there is a lot more in there, especially dealing with RLCs and different types of components that way. But this is the main focus for this section, and if you look at the practice problems, which I'll be assigning as homework, these guys is all that we're focusing on. And the nice thing is you've already seen these types of formulas pop up with 3.6. So this is just a continuation of it, and now we know how to deal if we have a non-homogeneous. And so that's the big thing, is knowing how to deal with those types of functions.